Welcome to our second lecture in Bio 156. We're going to be doing a little bit of chemistry this week in our lectures, and we're going to start out by talking about some things called atoms and elements. Now, the first thing you might be wondering is, hey, wait a minute, this is a biology class, so why the heck are we talking about chemistry? Well, the answer to that simply is that all living organisms are made up of these things called elements, and as a result, we should have an understanding of what the elements are so that we can understand how they interact together to help us form these living organisms. Now, by definition, elements are simply substances that can't be broken down into a simpler substance and still maintain all the properties of it. So, one example of an element is oxygen, okay? Oxygen cannot be broken down into some other thing that has different properties, okay? So an element, again, is a substance that cannot be broken down into a simpler substance. A related term you sometimes hear mentioned when we talk about chemistry is this term matter. And matter basically refers to anything that has a mass to it and that takes up space. And matter can be in the form of a solid, it can be a gas, it can be a liquid. It just depends on the particular matter and what the temperature is. Now, we have 92 naturally occurring elements on planet Earth, of which some, but not all of them, are shown in this partial periodic table here that I'm drawing a square around. Now, 6 of these elements are found in large quantities in living organisms, and they are 6 that you should know and be familiar with, and they include carbon, represented by a capital letter C, hydrogen, capital H, nitrogen, capital N, oxygen, capital O, phosphorus, capital P, and sulfur, capital S. There are also some other elements that we frequently see in living organisms, and you should also be familiar with these abbreviations. Capital N, small a, represents sodium. Capital K represents potassium. Capital C, small a, is calcium. Capital S, small e, is iron. And capital M, small g, is magnesium. And you can find these all in the periodic table. Again, this is just part of a periodic table you see on this page. But there is a larger version of the periodic table that is available, I believe, at the back of your textbook. Now, if we look at an element like oxygen, the smallest unit of an element that still retains all the properties of that element is called an atom. Okay, so the smallest part of an element is an atom. Oops, that should be element there. The smallest part of an element is an atom. And atoms have some unique characteristics and qualities to them, and there's a few terms I want to go over on this page that relate to those characteristics and qualities. Let me first say that every atom has some discrete subparticles to it, some little small pieces and bits. In the center of every atom, or almost every atom, there's a region where you find both protons, which are little subatomic particles that have a positive charge. You find neutrons, which are little subatomic particles that have zero charge. And you find electrons orbiting around that nucleus, and those electrons have a negative charge. Now, those atomic particles all together create a certain mass, an atomic mass. And this is not a weight, this is simply how much space do all of these particles together occupy in a particular atom. Okay, so atomic mass is the number of, and it's primarily the number of protons and neutrons, because electrons really, they're so dinky and they hardly weigh anything that their mass really doesn't figure into the atomic mass. So atomic mass is really protons plus neutrons together. Okay. The atomic symbol is the letter that we use to represent each individual element, like the capital C for carbon that you see here. The atomic number is this number down at the bottom here, the number 6 for carbon, and that represents the total number of protons present in the nucleus of that particular atom. Then the atomic mass is this number above here, which is a 12. Now, since we know the atomic number equals the number of protons, and we know the atomic mass equals protons plus neutrons, you should be able to figure out that there are 6 protons and 6 neutrons present in carbon based on the information you've been given. All right, now one other thing to mention really quick here is this idea of what's called an electron shell. Electrons orbit very rapidly around the nucleus of individual molecules, and they orbit at different elevations or distances from the nucleus. And each of those discrete distances at which different electrons orbit is called an electron shell. And I'll have more to say about that in just a minute. Now, before we talk about electrons and what their contribution is to the behavior of atoms, I want to talk to you about something called the mole. And I'm not talking about a little pigmented spot on your face, and I'm not talking about the mammal that digs holes in your yard. I'm talking about a unit of measure that's very commonly used in chemistry. It's a standardized unit, so that if I talk about a mole of hydrogen or a mole of oxygen, what I'm basically doing is talking about the exact same number of atoms of hydrogen and the exact same number of atoms of oxygen. Now, the number of atoms found in 1 mole is a big number. It's 6.023 times 10 to the 23rd. That means you're going to take 6,023, and you're going to add, let's see here, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 zeros behind it. So that's a really big number, okay? Way beyond trillions. Basically it's 6 followed by 23 placeholders after it, 6 times 23 zeros behind it. Very large number of atoms present in a single mole. Now what's interesting about this, if we think of this in terms of if we had little round things and we put them into a beaker, like let's say we have some purple beads here. Here I have 12, 3, 6, 9, 12, yep, 12 purple beads that I put into this beaker. Notice that they don't take up very much room because they're pretty tiny. By comparison, if I took 12 baseballs and put them in the same beaker, they take up a lot more room. And if I took 12 soccer balls, I wouldn't even be able to fit them all into a beaker. But regardless, I still have a dozen, don't I? Doesn't matter whether it's a dozen beads, a dozen soccer balls, a dozen baseballs. It's still 1 dozen, regardless of size. Okay? A mole is the same idea. Whether I have a mole of oxygen, a mole of iron, a mole of copper, they're all going to weigh differently because the atoms are different sizes. But they still all contain the exact same number of total atoms present in that standard unit. We're going to play more with moles later. You'll sometimes see books call this value of 6.023 times 10 to the 23rd as Avogadro's number. That's because Avogadro was the chemist who first came up with this idea of standardized unit of mass. And we will, if I remember to, at 6:02 in the morning on October 23, we will celebrate National Mole Day this October 23rd because that's 6.02 times 10 to the 23, October 23rd. Okay. So let's talk for a minute about another term you'll hear used frequently, particularly if you ever go into any kind of radio technology position, like if you're going to be an X-ray technician, for example. This term called isotopes. And what are isotopes? Well, isotopes are, in essence, they are different versions of the same element that have different mass number. And it's not because they have a different number of protons, but rather because they have a different number of neutrons. And I need to back up here for 1 minute because I just realized I forgot to mention something to you that's very, very important. In any atom, the number of protons will always equal the number of electrons in a stable atom. Okay, the number of protons equals the number of electrons. So if you're given the atomic number, remember atomic number is the total number of protons. If the atomic number is 6, then the number of electrons present has to be 6. Okay, now let's go back to isotopes because this is where that becomes relevant. Let's take carbon. In its normal state, carbon has an atomic number of 6. That means it has 6 protons. That means it has 6 electrons. And it has an atomic mass of 12, meaning, and remember, atomic mass is equal to the number of protons plus the number of neutrons. So if there's 6 protons, that means there must be 6 neutrons. Now, carbon can also come in some other forms, in different isotopes. Those isotopes still have a total of 6 protons, which also means they have 6 electrons. But where they differ is in the number of neutrons they have. One isotope of carbon has an atomic mass of 13, which means that instead of having 6 neutrons, in this case it has 7 neutrons. Okay? And then there's another form of carbon that's actually radioactive. This isotope has an atomic mass of 14, which means it has 8 neutrons along with the 6 protons and 6 electrons. Okay? So isotopes have a different number of neutrons, and they have the same atomic number, meaning they have the same number of protons, they have the same number of electrons. Okay? And they have a different atomic mass. Now, isotopes, especially radioactive ones, can sometimes be used as tracers in things like MRIs, like you see in this picture here. They'll use radioactive iodine, for example, and trace it in the body to find the location, for example, of tumors or masses or growths, for example. All right, next thing I want to talk about is how are electrons arranged inside of an atom. Now, remember I told you that an atom has a nucleus, and that nucleus contains protons, and it usually also contains neutrons. And then I told you that the electrons orbit around that central nucleus. Let's take the simplest element out there, which is hydrogen. Hydrogen has an atomic mass of 1, and it has an atomic number of 1. That means it has 1 proton, it has no neutrons, and it has 1 electron. So here it is. You can see 1 proton in the center, 1 electron orbiting around it. Now, notice that that 1 electron orbiting around the hydrogen is all by itself. If I went to helium, which is the next element, helium has an atomic number of 2, but it has an atomic mass of 4. That means there are 2 protons. That means it also has 2 neutrons for a total of 4. And then orbiting around the outside of it are 4 electrons. And here's 2 of those electrons. The other 2 electrons orbit around at a greater distance from the nucleus. Okay? And the reason for that is there literally is not enough space this close to the nucleus for more than 2 electrons to be orbiting in that space. Okay? So this first energy shell here, the one that contains 2, always only contains a maximum of 2. And that first energy shell is also called the S shell if you've ever taken a chemistry class before. It always holds 2 electrons and only 2 electrons maximum. Okay? Now, if we go to something like carbon here, carbon has an atomic number of 6. It has an atomic mass of 12. Means it has 6 neutrons in the center, 6 protons in the center, and it has 6 electrons that are orbiting around the outside of it. 2 of those electrons will be in the first energy shell. The remaining 4 electrons orbit at a distance farther away from the nucleus where there's more space for electrons. And as it turns out, this second energy shell can hold up to a maximum of 6 electrons. Is that right? No, it's 8. Sorry, I shouldn't second guess myself. You can tell I'm a biologist and not a chemist. Okay, it can hold a maximum of 8 electrons total. Then the next shell out is called the third energy shell. After I get 8 electrons, and let's look at phosphorus, for example, here. It has 2 electrons in the innermost energy shell, or the first energy shell. In the second energy shell, it has 1, 2, 3, 4, 5, 6, 7, 8. That's all full. So any additional electrons have to move out to a third orbit where there's enough room for them to occupy space. And that third energy shell, for the purposes of our class, we're just going to say that it can hold a maximum of 8 electrons as well. Okay? Now, there's something called the octet rule in chemistry that's very important, and we will play around with this in class. The octet rule basically is what predicts how different atoms will bond with each other. And the general rule of thumb is when 2 or more atoms get together to form a molecule, they will do so in such a way as to try to fill up their outermost electron field so that they have, for example, a total of 8 if it's the third or the second energy shell, or so that they have a maximum of 2 if it's the first. So let me give you an example here. Let's take oxygen. This Bohr diagram, and by the way, that's what all of these drawings are, where you can see the electrons circling around. Bohr diagrams show the number of electrons orbiting around the center. In oxygen, we have a total of 8 electrons. 2 are in that first energy shell, and that first energy shell is the only one that does not obey the octet rule. Okay, you can only have a maximum 2 in that level, and then it's filled because there's no more room. Then in the next, of the 8 electrons, we still have 6 more that have to go somewhere. So they're going to go to the second energy shell. 1, 2, 3, 4, 5, 6. Okay. Now, by the octet rule, oxygen can basically take on 2 more electrons somewhere in that outermost energy field. And the way it does it is if we take, for example, a hydrogen with its lone 1 little electron, hydrogen can share its electron with oxygen, and in doing so they form a bond. And another hydrogen over here could do the same and share its electron with hydrogen. Now with oxygen, I mean. Now my oxygen has a total of 8 electrons in its outermost energy field because it's sharing electrons with hydrogen, and as a result, it is now stable and happy. It has achieved the magic number of 8. Now hydrogen, remember, is this unique atom that has only 1 electron, and it needs 1 more electron in order to be happy. So for it, it's happy because it's gotten its second electron by sharing 1 with oxygen, and now its outermost energy shell, the first energy shell, is filled at 2, and it's quote-unquote happy as well. Now, if that doesn't entirely make sense to you, don't worry, because there are some tutorials available online in the class to help you learn this information, and we will be spending time on it in class to help you work through your points of confusion. But this just gives you your first exposure to the material, so we have something to work with in class. All right, that was it for the first part here, I guess. We're going to be moving on in the second part of this lecture to talk about a little bit more about molecules and the bonds that form to make molecules. So I'll see you there.